Right, so thanks for having me here. It's sort of weird giving an external talk inside an office that I understand very well, yet I've never been here, so it's it's very perplexing. So I'll be talking very much about Google stuff, and I'll be giving an introduction by sort of a historical overview be on our recent work on Farfield, figuring that this is of most interest to the audience. I'm very proud of that work. I think it's in a good sort of mature state, so I think I have something to say, but you guys can give me feedback on that. So a little word on credit. So there's a lot of people involved in this. So the people listed here are the main stars that did all this Farfield work, and so that's why I highlight those. But for the other stuffs,
It's not working.
the mic is not working.
No, you can't hear the back.
Is there still a support person? I do see the view meter going up and down, so I think I'm producing something. KK is on it, so I'm just going to keep going. I'm speaking. It will get worked out. So at least here in the room you can hear me, right? Yes, very good. So there's lots of people in the speech group, and this is covering a very long time. The other thing is I want to make sure is this is very much a Google perspective thing, and so I'll just be talking about that. Not that we think this is the only way of doing things, but there's definitely a lot of work that has been done before. I have to hold this as well. I'm not going to make an attempt to give you guys credit because there's too much stuff. But at the end of the talk, there's paper references that I think have ample references. So please feel not that we are ignoring you. So to get started, a lot has happened in speech, and that's why I don't like historical overviews, but in this case, I think it's sort of appropriate. And I think the best way of putting it is the difference between 2006 and 2011. So this is on national broadcasts in the US, and I still find funny.
Hi, I'm Julie. Nice to finally meet you. I haven't been on a blind date in a while. So, Doug told me you work in customer service.
That's right. I do the voice recordings for companies such as United Airlines, Blue Cross, and Amtrak.
Wow, Amtrak, huh? Well, then I guess I have talked to you before.
I'm sorry, I didn't get that.
Oh. Nothing, stupid joke.
Hey, can I get you something to drink?
Oh, what do you think, Julia? Latte or cappuccino or something?
Did you say latte or cappuccino?
I said both. Do you want a latte or cappuccino?
My mistake. Cappuccino would be great. Gary, before we go any further, let me get some information.
Sure.
Please say your age.
Oh, yeah, I get that a lot. I know I look young, but I'm actually 29.
I think you said 19. Did I get that right?
No, 29.
I think you said 9. Did I get that right?
No. Wow, 29.
So, you get the idea. So this is the worst possible state, I think, to be in terms of technology, because they're not even making fun of us. They're just doing exactly what our product was. And, this is 2011, popular press. And you can see, people suddenly go like, the speech recognition thing is great, right? So there's been a very big change, I think, in the perception of what we do. And Google has sort of lived through that revolution. And in that sense, I think the historical overview might be of some interest. So, a couple of things that we did early. So again, you have to put yourself back in the time, and people have a hard time doing that. So in 2005, there is no smartphone, right? So the internet is everywhere. Everybody knows Google, but that's on your desktop. People have a cell phone, but that's a phone, nothing else. And so while walking around, you want to call your restaurant, and you need the number, right? And there's no internet to really get that. So in the US, there's this 411 service, which most people just hate because it costs $1 to ask, to get connected. So we set up this automatic service, and rather than the woman at the bank, giving you abuse so that you can't talk to a person, it would actually help you make a phone call. Initially, very popular because it saves you the $1, but eventually people sort of realize that it can automatically dial something by just saying the name of the business, and we look better, I think. So another thing we did is play with voicemail. So voicemail was still in that state where press 7 for the next message or whatever, and then the phone number comes and you just missed that, and then you have to replay the entire thing. And so making that transcribed, even if there are errors, you might get the number right. And then with Google Voice, you can do some information extraction, maybe click on the number and dial people back. And so this had some interest. Something we're still playing with that is More fantastic is sort of subtitling YouTube. This is very hard, so the word error rates are still very high. But if you integrate this with translation, you have a nice vision of being able to watch any TV in any language from anywhere. And those are interesting things. The other thing that you can see people, it's not just speech recognition that gives you the transcript. A lot of people are not really unwilling to put captions underneath, particularly if you can translate it. But time coding it is very painful for a person. Whereas in our view, if you know speech recognition, forced alignment is not very hard. So we provide this as a service, and it makes it very easy for people to produce transcripts if they just have the text. Right? But these are all sort of fringe efforts now, because the big revolution was, of course, the advent of the cell phone. Launched in 2007, both Android and the Apple phone, and typing at these things is a pain. Right? Dealing with a little keyboard, it's very hard to deal with, and suddenly speech is something that is considered to be much more pleasant. And you can see how much traction this has. We get about a century of speech each day now through these systems. And this is unlike Julie by choice. You're not being forced to use it because you can still type at the keyboard, but it comes in 3-second utterances, and we have it in many languages and so forth. So this was really a revolution. So a very simplistic but not unfaithful representation of this system is really, it is sort of speech in, answer out. Right? So you have your, if I can point at things, which I can't. So you have your mobile device, and you talk to it, and we stream the audio to a recognizer in the cloud somewhere, and it does something and gives you the result back. And sometimes it really is just literally speech recognition. So if you dictate an SMS, you just want to text, and that's exactly what it does. But sometimes it can become more complicated, right? So if you do a web search, it needs to be integrated with web search and do the search and give you the search results rather than anything else. If you're driving and you do something with maps, maybe the answer is actually speech, so we need to do TTS. And then in terms of recognition, it can become more complicated, which people don't really appreciate. But if you have friends, unlike me, they might have peculiar names that we might not really put high on the list of people to recognize, but they're very important to you. So sort of at the last moment, we have to splice in your context or make them more likely so that we don't screw up recognizing your friend's name. And so those are complicated things to do. The other thing is, if you're driving or want to interact with one of these devices, you want them to wake up without having to futz with it. So the hot word thing, OK Google, when the thing turns on, is a complicated thing because it has to run 24 hours a day. We don't want to eat up your entire battery in an hour to do so. And so there's a lot of stuff around that. A lot of it is engineering. A lot of it is also science. So I'm going to just focus on the speech recognition part because I assume that's what of interest to the people here. So there isn't really much, I think, peculiar in the whole setup. So we use finite state transducers to go from the lexical to the acoustics. And there's a language model, which is still just an n-gram. We have a lexicon to map things, and there's an acoustic model. There are little bits that I think are warrant particular attention for the things that we do. So in the language model, we have a lot of times and dollar amounts that you would like to present in a way that is normal to people and not start spelling out $3.59 and so forth. Like I said, the dynamic stuff is important. So if you are at some dialogue state where you can only say a couple of things, we don't really want to run the large vocabulary and get it wrong. Yet again, you might have the freedom to say something else. So you want to sort of bias things to the terms that are likely to appear without making it impossible to recognize anything else. Like I said, contact names are important and tricky to do, but it has to happen. Text norm is important. So I challenge you to say what it says. Yes, it says "Go Red for women," not what you thought it was. And then we just have the acoustic modeling stuff. So I am going to focus on the acoustic modeling stuff because there's sort of a tandem revolution going on in terms of deep neural nets and this application stuff. And more geeky and I think well presented is in this paper. So we sort of have this positive feedback loop going on where people love mobile speech and interact with it a lot. The centuries of data coming in is evidence of that. And initially we had the GMM technology, which I think is faithfully represented there, sort of converged at some point where more data really didn't help that much, right? So if we had a system based on that and you get more and more data, there's not that much you can do with it. Yet the neural network revolution, if you want, or the resurgence of it, is pleasant in the sense that we can make bigger models and they really improve. Right? You can see here from 500 to 2,000 hours, there is still a nice gradient in terms of word error rates. So there's hope we can do more stuff with it. So this is a very nice setup, right? So people like using this stuff and give us more data, and because of more data, we can try to make more accurate models. And this is a good loop, and very much unlike Julie, people are appreciative of us, and we do better. So it's a very happy time to be in speech recognition, I think. And so digging a bit more in the neural net revolution, of course. Well, I think most of the room here wasn't born yet when this was, but it's not new. It was in the early 90s, very quite popular, and but it sort of came back, and I think it started with students that in around 2009 showed quite promising results on timid. And as usual, we are skeptical, but a bunch of them did simultaneous internships, I think at IBM and Microsoft and at Google, and all showed very promising results. So I think we all were excited about that. And I think a turning point was Frank Seide, who gave a talk at some point on Switchboard, really large vocabulary, and showing that this stuff worked really, really well. And I think everybody got extremely excited about this. And we really jumped on that. And I think we were one of the first to put it in products. So, within a couple of years, the revolution was on. And as you noticed, I think there are very few, if you look at the conference that we just passed, I think there are very few GMM papers left. So, some early things that we saw. So these are very old results, and I wouldn't read into too much. But you see big gains going from GMM to DNN on voice search and also on this YouTube task. We have large databases there we can play with. They were also extremely painful to deal with because on a GPU, as you can see, one epoch takes 320 hours. That's painful to run, right? And but then, the paper down there, we have the Brain Group, who started this thing called Disbelief, and this is this paralyzed trainer based on the Hogwild algorithm from, I think, Michigan University. And this is what is now, it's been rewritten and transformed and is now TensorFlow. And it's open source, you can get it at home, but it's exactly the same underlying thing. And that made it still painful, I think, in my view. But the 85 million parameter was sort of our usual DNN at some point, which is twice the size of the things that I'm showing there. And with this, we could sort of train 10 epochs in 10 days, which is painful, but not too bad. And then, of course, the sequence modeling quite quickly came. And I like this presentation of sort of how to think of it. So it's essentially a feed-forward DNN, if you can think of it, and which predicts from the acoustic observation X to the probability of the state given X. And instead of just doing this feed forward and independently from frame to frame, you have as output and input a state, which carries over from time, and this becomes a recurrent network, right? And therefore, your backpropagation learning is not just from the output state towards the input. Now it goes backpropagation through time. And these models, of course, were also not new and very well studied before. And something that's very hard to practically use them is this backpropagation through time. You have the vanishing or exploding gradient, as I like to say. So just like a series, it converges, but doesn't do anything for you anymore, or it becomes unstable and explodes. So also an old model, but that was picked up and is now quite common, is the so-called LSTM. And I'm not going to go into too much detail, but you see a similar, it would be nice if I have a pointer here. But do we have one? If you can get me a pointer, I'll talk through this one, but maybe I have something else to point out. So you see the recurrent state there at the bottom, and it comes in with X at the beginning. But in addition, you have these gates, the forget gate, input and output gate. So there's this notion of a cell which keeps some state. And then the forget gate allows you to learn how much of the information should leak away. And then the input and output allows you to control how much information is coming in and going out. And this it's a nicer model, of course, and but it's not that much more complicated. But I think the big boon for us is that it trains much better because it sort of it balances the input of the gradient over time, which is something that we appreciate in terms of training these things. So you can play with those. Oh, so something I should say. So the network blows up dramatically if you go from the recurrent state to all the other gates and inputs. And so controlling that size is a good way to control the parameters. So what you can do is have this projection layer that goes in between recurrent and output, or is directly the output. And like that, you can control the parameters. So this is some of the early work we did. So as a reference, we have our, at that point, usual model. So that's the 85 million parameter 8 by 2560 hidden DNN, which reaches about 11.3% word error rate on this task with CE, and then goes down to about 10.4 with sequence training. And then in the top one, you can see sort of a pure model where you can change the number of cells in the layer. And you can see, and you can have the depth, which is the number of layers. And you can see you can sort of keep the 30 million parameters there by changing the width and depth. And you can see that word error rate-wise, you already beat the DNN at some point. And then with the projection layer, you can have a wider layer, but control it because of the recursion. And you can sort of keep similar number of parameters. As you can see, you can get about 10.7 with 30 million parameters, which beats that system. Of course, this is a recurrent model, so it has state. And the danger if you're training it is that it's not just learning the acoustic model, but since there's a sequence in there, it's beginning to eat into the language model, right? So something that's interesting to look at is particularly here is to do sequence training, where you have the recurrent model with the sequence objective. And as you can see, it occludes here, or you can see it over there. So, 11.3 at CE for DNN sequence training, you get a nice gain, but you see that the gain holds for an LSTM even after sequence training. So we like those models because they're smaller and they behave well. So then, of course, engineering sets in, and if we have multiple toys, why not put them all in together in one toy? And so the CLDNN was born, and this is sort of optimized. So this has a convolution layer at the beginning. I'm not going to talk much because it will come back. We have a number of LSTM layers and a DNN. And as you can see there, we get gains out of this, which hold up after sequence training. So from 14.6 to 13, and similar 13 to 7.7 to 13.1 on a clean set. And in noisy conditions, we similarly keep a gain. So this sort of became our, I don't want to say our workhorse, but sort of the model that we like and that you've been talking to, hopefully at some point. And so this is our CLDNN that maybe will have recurrence in this talk. So a bit of yes, thank you. Yes, well, it's not very.
It's not very bright.
All right, I'll do my best. So something else I've been playing with. So things are changing because of the recurrent models. You have a state, and certain things that were optimized are not optimal anymore. So with an HMM and a DNN, we usually use 10 millisecond frame rates. But since the model has no memory, that is sort of optimized for that. And we actually can get away with lower frame rates, which is nice for us because we have to burn fewer computers and get less latency. So on top there, I know it's unreadable, but the green line is a 10 millisecond system, and then the red one is one with 30 millisecond frames, and that the real time is the x-axis. So you can see we get sort of the same performance, even though we compute 3 times fewer frames. And then something else that has become popular is CTC, and I've tried to explain it on the left there. So if you think of the probability of the observations, the marginal across state sequences, and the summation over all possible state sequences, if you think of an HMM on the left there, you have a little AB model there. And if you take into account the HMM model assumptions, the independence given the state, and the Markovian assumption on the state transitions, you get that sum with the product. And we know this all very well, and we can compute this exactly and efficiently by the forward-backward algorithm. So in CTC, we introduce this blank symbol, which is the little hyphen over there. And so the probability of a sequence is any possible alignments of the blank and output symbols. And if you make an independence assumption of the state, then you get something that looks very similar to the HMM case. And again, with forward-backward, you know how to compute this very efficiently. So what is nice about this model is that if you look at how it behaves, and that's sort of at the bottom right there, you see it outputs blank most of the time, and it has these spikes for the different symbols that it can output, and it has the freedom to put them wherever. And this also helps in terms of speed and latency, because in decoding, if something is very spiky, you can get away with lower beams, and it helps us. The only problem is that if you let it go, it has the freedom to output spikes wherever it wants. So sometimes it puts everything at the bottom. So at the bottom graph there, you can see that it squishes a lot of the outputs, which is bad for latency. But we can sort of constrain it in doing the forward-backward to not consider things too far apart, and then they behave nicely. So something else we've been working on is, and a lot of work has been done in Aachen on this as well, is this raw waveform processing. So this is where the neural network will take over the universe and starts at the bottom by trying to take the feature processing into account. So the idea is here on the left, you can see the entire model. So hopefully at this point you recognize the CLDNN, which is that model, and we have an additional convolution box, the blue one at the bottom, and that's sort of highlighted here. So rather than inputting null features, we input the a piece of the raw waveform. So you see the M samples there. Then we define P trainable filters, and we convolve the input samples with those filters. Then we do max pooling across the output of that and apply a nonlinearity, which gives you some kind of frequency representation as depicted at the bottom there. And since this is now all differentiable and integrated in a network, you can backpropagate the actual classification error towards the feature extraction and learn this. And it's sort of magical because this is the Aachen people found this, and you learn some of these narrowband filters, and they distribute sort of along the lines of what we have optimized in other ways along the MEL or gamma tone, and you can see sort of the distribution of the filters there. And so it puts a little bit more filters on lower frequency we usually see, but it looks very similar in terms of the distribution. And then in the table here, again, you can sort of play with it. So the notation there is, C1, L3, D1 is a system that is one convolutional layer, 3 LSTM layers, and one DNN layer. So the early work, I think, is the bottom one, which is D6, right? So just a DNN system. And there you can see log-mel versus raw, you lose a bit, even if you try to cleverly initialize these things. But if you look at the ones that have recurrent layers, so all the ones that have Ls, you can see the L3D1 RND, which is completely randomly initialized, which learns a system that is equivalent to the log-mel. So that's a very nice setup because you can just let it go and it will come up with something. All right, so I'm going to now transition into the more meaty part of the talk, which is focusing on Farfield. So you recognize the cone there. So this is a whole new way of interacting, and people seem to really like this. So rather than pulling out your phone and being antisocial, staring at your phone, you can actually, it's in the house. You can just talk to it. You can command the computer to tell you something, and that's sort of a cool thing. The problem, of course, is that most people are unlike us. They have no idea what speech recognition is. So if it works on my phone, why wouldn't it just work across the room? I don't see any difference here. It's the same thing. And of course, this is very not true, and that's a big problem for us to solve. And so we've been very busy with that. So in terms of approaching this, since we have no launched product, we have no data, and data here is complicated because it comes in many forms, many different kinds of noise, many different kinds of reverberation, and how do we deal with this, right? So we do, of course, have prior data. In fact, we have lots of data, but they all close talking from a phone, right? So the approach that we've been taking is to build a room simulator, and there's a well-known, not to me, but somebody in my group, image method, which basically it's like ray tracing for audio. So it has a fairly simple model of a room, and it produces, you can position a microphone somewhere in the room and compute the stylized response you would get for some speech. And so we sort of, when I talk about clean, I'm actually talking about the data that we get in from the outside, which actually isn't clean. It might be reverberant, but for the sake of this discussion, clean is the source signal that we get from there. The reverberant cases are the simulated ones. So for the training set, we have a 2,000-hour set, and we made up 100 different room configurations that we think are sort of likely of a room you might live in. So no operas or things like this, but sort of looking at your living room being small or big. T60 reverberation at reasonable levels, and we sort of simulate this 8 mic array at that point with 2 centimeter spacings, and have various locations for the speaker and noise sources. The noises we use, we have this, one of our engineers has a daily life, so he could record it himself doing the dishes and so forth. So that's sort of home noise, and then we have some YouTube stuff that we mix in as noise sources, and then SNR distributions from 0 to 20 dB. So for test set, we I think did something more interesting. So we have the usual test set that we also use for voice search. That's 30,000 utterances, about 20 hours of data. And so we can run this through the simulator, obviously, to get something that is matched but simulated. So the other thing we did is we took that set and set up in an actual physical room. And then we have one of those mouth simulators, and we play back the queries from the mouth simulator and record it on an actual physical mic array. And there, of course, you can change the room very much because it's fixed somewhere, but it's more realistic than the simulated data. So I'll be mostly talking about simulated data until the very end of the talk, where I'll give you the re-recorded stuff just to sort of as a validation that we don't overtune on things. A little truth in advertising. So I'll be talking a lot about beamforming and things like this, but the massive gain comes from multi-style training, which people tell me is abbreviated as MTR. But so on very early work still with the DNN, so this is not the same task. We got from a clean system, so a clean training set, where clean means the actual recordings, and clean test set 16.2. If you get the noisy versions of the test set, it almost doubles. But if you train on an MTR set, we get a lot of it back. And so this is on top of a very optimized MTR trained system. So anything I talk about here is smaller gains, but they're much harder to get because the initial model is already quite noise robust. So getting a bit in multi-channel, and I think you guys know more about this than me, but I'll try my best to convey what I think I know. So generally, enhancement is done separately from speech recognition, and so the common thing is to do it in 3 stages. One is a localization stage, where you try to find where the source is coming from. Then you do some beamforming to try to enhance the signal coming from that direction, and maybe some post-filtering. And so in the equation there, you can see we have signals coming from C microphones, X of C, and then you have from the localization, you get some steering delay, which gives you an indication of the angle of arrival expressed at that time delay tau C. And then you do a filter of the different channels and sum it, which gives you the enhanced signal. And so commonly optimized with things like MVDR to compute the filter weights. So to connect to my lengthy introduction, I talked a lot about the learning the front end. So you can extend that quite easily to make this sort of fit multi-channel, right? And this is sort of our first step at doing this because it's easy to do. So the assumption here is instead of doing the steering delay and the localization explicitly, we do this implicitly in the network. And we do so by, as you can see, we have a similar beamforming equation up there, but the steering delay is taken out because it's considered to be implicitly done in the filter, right? If you move the filter tabs, you could have the steering delay. And then we factor it in the sense that we give it P of such filters that allows it to learn different steering directions and optimize the filters for it. And that would fit in the raw waveform setup. So again, you'll see, hopefully you'll recognize the CLDN with the angle bracket over there. And the thing before it is very similar to the raw waveform filter learning, except it's multi-channel, right? And again, since it's now all integrated, we can do this joint optimization. And so again, this is not novel. In the GMM world, there's the Lima Bean stuff that has attempted very similar thing, but this is in a DNN, which makes it somewhat different. So first of all, it's interesting to see that if you look at the learned filters, even though this is independently, it still behaves in a very similar way. So you can see for the 2-channel setup here that the filters look very similar to what we learned for the single channel case. And the other thing that is nice is that you can see if we increase the number of filters and increase the number of channels, we get a nice gain over by increasing those, right? So it seems to be learning something, and that was a pleasant surprise. So trying to analyze it a bit, because this system does a lot, right? You just give it multiple channels, and somehow it figured out how to do the enhancement and the recognition. So trying to sort of piece apart a bit what we're learning here. So one thing is, does it indeed make good use of the phase to try to do beamforming, right? So one thing you can do is you can take a log-mil setup, and you can just increase the number of filters to see if it just learned from having more filters, right? And you can see we get a bit of a gain by going from 128 to 256 filters, but repeating the results from the previous slide, the raw waveform thing, you get a significant bigger improvement. So it seems to be using some of the information there. So the other thing that it does, like I said, implicitly does localization, right? So since it's implicit in the network, we can't really analyze where this happens exactly, but you can cheat it by saying, I'm giving you the oracle information to sort of compare it, right? So the first line of this is where we do oracle delay and sum. So since we have a simulator, we know exactly what the angle of arrival was for the data, and we can time shift it such that delay and sum would be one approach. As you can see, we get some gain going from a single channel to multiple channels, but it's not as big as with the other approach. So the second line there is where we give it more chance to do some of it work, but we still give it the steering delay. So what we do is we take each of the individual channels and we time shift them such that they would be aligned exactly according to the steering delay, and then let the network do. And as you can see, it does as well as the non-cheating setup, which is the last row, where we don't give it any kind of time delay of arrival information, and it seems to be quite effective at learning that. So it's nice to see that it learns beamforming and the localization implicitly without giving it any kind of Oracle information. So analyzing it a bit more in terms of quantitative, like on the left-hand side here, you see a breakdown of the word error rate according to the various dimensions of distortion. So the top one is SNR, from very noisy to less noisy. And then the blue line is the one, I know it's hard to read, but the blue line is the one channel, and then the other ones are multiple channels. So you can see, as expected, you gain more on the noisy cases than on the not so noisy cases, and you get more gain if you have more so than the change from 1 to 2 channels. And similarly, the second one is the reverb time. So you can see over any possible reverb, we gain more or less the same thing, as well as the target to the distance. So the other thing that's cute of this setup is that we still have an interpretable filter on the input, right? So we know that these n loop directions that we seeded in the input layer, we can take the weights out of this and analyze them. So what you see here is a beam plot. So on the little colorful things on the right, you see the angle of arrival at the y-axis and the frequency response along the x-axis. And sort of surprising is it doesn't really do spatial filtering. You see it's very frequency specific, right? And that is, this is the downside of neural networks. We don't really know what the rest of the system does with it, but apparently it likes this presentation because, of the word error rate results. And so that sort of gave us some food of thought, but sort of to summarize where we are at this point. So you can see the results there. We like to see how things behave after sequence training, because that's more of the mature system. So you can see gains hold nicely. You can see the Oracle MPDR and delay in some results, which give a nice gain over the single channel. But if we do this raw vector system, particularly with 4 channels, we get quite a nice gain over that. So the extension is sort of, we want to encourage it to be more along the lines what we envisioned this doing. So we can factor the spatial and frequency filtering to some extent. So what we do here is we have P look directions and give it very short filters of 1 or 2 milliseconds. And then do the second convolutional thing, which is the purple box in the middle there, where we do the frequency analysis. So this is very similar to the raw waveform thing. The initial filters are encouraged to do spatial filtering. And so if you look at whatever you do, if you train this, you see something that looks more what we intended to. So you see a lot more spatial filtering because of the stripes in there. And but still, you see some filters coming up with specific frequency responses. And so it's a different solution, but it seems to work. So if you look at the word error rates of these models, so the 2-channel unfactored you see there, if you give it very few spatial filters, it hurts you. But if you give it more, you improve over the initial structure, because apparently you encourage it better to do spatial and frequency filtering. Again, you can do a control experiment. So you can initialize these spatial filters to be exactly delay in sum. So if you put one filter with an impulse at 0, and you put another one in an impulse delayed, you basically give it a particular delay in time of arrival. And as you can see, if you do this fixed, you don't get as good a system as if you then let it train. So with 5 look directions, you can see we get an additional gain of 1% by letting it train. So in summary of this, so unfactored to factored is a gain, and again, it holds up after sequence training. So this is a nice result in that sense. So yet another, so this is more complicated because it's, I think, a bit more recent, but trying to talk through, here the pointer. It's a very small dot. So essentially here you see exactly the same model we had before. So we have a CLDNN on top here. And instead of now doing the factored input that I just described, we're saying we only do one filter and sum implementation at the bottom here. So we have the 2-channel X coming in, and they're getting filtered and summed and put up into the system. So instead of now factoring and having many of these, P of these explicitly, we only have one of them. And the thing that is different is that the weights of these filters are adaptive over time. So the weights are predicted by this little LSTM fantasy down here. And that also operates on the input signal and through a gated feedback. I'm not going to go in detail. There's a very good paper that was presented at the conference here that describes it in much more detail. So the gated feedback and the signals come into this filter prediction LSTM. And the filter prediction comes up with the filtering weights for the one that actually does the beamforming and enhancement here. And so if you look at this, first of all, it works very well. So you see here down the CE performance and the sequence training performance, which is on par with this factored raw waveform system that I just described. And in terms of operation, it's sort of interesting to see that even though it has more parameters, because it's a little LSTM, you can see 18 versus 24 million parameters, it has fewer multiply and adds because they're not convolutional and therefore more efficient. In terms of the way it behaves, you can make nice plots. I'm not sure what to interpret from this, but on top there you see an example of an utterance, the noisy one on top, the clean one at the bottom, and then you can, since you now have a dimension of time, you can look at its response in a particular direction over time as it goes over frame by frame, predicting the filter. So now we have sort of three models, right? And they're all in the time domain. So we have the factored raw waveform model, and we have this adaptive raw waveform model. But they're all still operating in a time domain. And something that's painful, no matter what they are, is that it's expensive to compute them in the time domain, right? So as we all know, there's the time versus frequency duality. So can we frame these exact same models in the frequency domain, and how would those behave, right? That's the what we're trying to make use of in the next stage. So again, now the same picture. So again, we have the acoustic model on top here, the CLDNN, and we have this factored structure here that I just described. So if you think of it, instead of taking the raw waveform signal coming in here, you can compute the complex FFT. And then to apply the short spatial filtering here, you can compute the complex factor, and then it becomes a pointwise multiplication to implement this. So this would give us our signal up here. Then, one way to implement this is to do the frequency analysis, and then there's no real equivalent of max pooling, what we've been doing in the time domain. So you could go back to the time domain, do max pooling, and then go back, but this would sort of defeat the purpose of trying to do things in the frequency domain. So we sort of have two ways of approaching this. One of them is very akin to Bell filtering. So we take the log magnitude, we take the magnitude spectrum, and then apply the filters on that. The other thing which was presented at the conference here by Esa and Bacchiani is you can do what we call complex linear prediction, where we take complex filters here and then take the log magnitude, which is shown in the paper the same as average pooling instead of max pooling. And again, empirically, that seems to work reasonably well. And again, so we had this other model that's described, which is adaptive. So of course you can do the same thing. But now in the filters that are predicted here are actually complex filters that are applied to the complex FFT that comes in here. So the big difference is that if you look at the time domain spatial filter that it's trying to do here, you get something like 25 taps that you try to predict. Whereas if this model wants a 256 FFT input, the filter now has to predict for 2 channels and complex, so 4 times 257 weights. And that's a much bigger number to predict than it is in the time domain. So looking at performance of this, so the, what I forget to say here. So once you are here, you can still do the same thing where you can do linear prediction of energy or complex linear prediction, just as you would do with the raw factored system. So looking at performance, we sort of gave up on the adaptive thing because you can see you could do this dynamic beamforming with the linear prediction of energy, but even the complex linear prediction, we already see a degradation, again, likely because it has so many weights. But if you look at the factored case, the complex linear prediction or linear prediction of energy, we get decent performance for either. And it behaves very well in terms of compute because they're not, you get rid of the convolutional filters. And this, in fact, allows us to increase the filter size and the FFT size with a very gradual increase in terms of compute. So as you can see here, this highlights that if you do this in the raw time domain, we get 17.1 with a whopping 53 million multipliers it adds. But if you do this in the frequency domain, you can see this is much better behaved, and we actually get a gain by building the bigger system. So if you look at what's learned on the left here, you see what we learned in the time domain. What you see on the right here is what we learned in the frequency domain. And it comes up with a very different solution. And again, a problem here is that it's a neural network. So there's a giant system on top of it, which has recurrent layers and so forth. It has far more parameters than what's on the input. So what is the best matched condition? It's part of it, how you train it likely. And so that's very hard to get insight into, why this representation, it's equivalent apparently in terms of performance. We get more or less the same word error rate. But to make sense of why this is good for the system is, something we can't really answer. So as I promised, so all of this was on the re-recorded sets, and it's nice because it allows us to do these, somewhat insightful experiments where we know exactly what the time of arrival was, and therefore we can take things out. But of course, the thing we want to really use is in real life. So this is the re-recorded sets as I introduced. So we have the clean recordings, which are just voice search utterances, which we replay through this artificial mouth. And then we have this set up in a sort of a fake living room. So there's on the coffee table, there's a coffee table in front of a TV. And so we put the mic array on the coffee table or next to the TV stand. And then we play back these queries through the artificial mouth. And we can play back the noise through the artificial mouth as well, and then sort of get different noise conditions. So you can see here, clean is where there's no noise mixed in. Noisy is where it is mixed in. I don't know what ref stands for, but it's either on the coffee table or the TV stand. And so as you can see, the one channel raw system gives us some performance. Then the unfactored and factored, you see the gain remains. We get an additional gain. And then computationally efficient, doing the complex linear prediction, we actually get a nice result. And if you look at the performance of the NIB model, which is included here, it doesn't do as well, again, given the size of the filter. So I hope I didn't bore you too much, but so I think the historical overview, you can see there's some kind of consistent path where we try to keep hammering on the same stuff that we have. And so again, I'm not saying this is the only way to go. I'm just giving you the very personal view of what we've been doing and why. And with this new Farfield stuff, we sort of naturally extended the models that we already had and tried to enhance it in such a way that we can make good use of the multiple channels. And I'm quite proud of that work in the sense that, it seems to have nice properties of the time domain versus the frequency domain, factoring versus doing it adaptively. And I think the end-to-end fantasy that is popular is not relenting, because you see the front end has sort of been eaten up. Maybe enhancement is eaten up by this kind of approaches, and God knows what goes on after that. Thank you.
Questions?
Well done.
That's a microphone, so who wants to ask a question?
If we switch to human listeners, the knowledge of the semantic field of the topic allows humans to go from 10% word recognition to 90% in very noisy conditions. Do you think that using comparable information might help?
I'm convinced, because I think that's good evidence that it does. But do we know how? I don't know.
So you're not working on that?
Well, if we had a direct model that we could apply now, I would definitely be trying it. But I'm not sure that we have any ideas. And I think incrementally moving from things like this, we know how to sort of manipulate this and look at it, right? It gives us some improvements. It's more marginal and maybe less out there, but it's practical. And if you have a great idea, please tell us. We'll try it.
Yes. So I didn't hear about the echo cancellation. Can you quickly explain how do you combine echo cancellation with your deep neural net beamforming?
So the approach we've taken, and given that it's as successful, we have made as much implicit as possible. So initial things, of course, we looked a lot at the, I don't want to say traditional, but there's a lot of stuff there that has been written that makes a lot of sense and it actually works, right? But practical applications is hard. So if you think of doing beamforming, you need localization. So if you look at how a localizer behaves, sometimes it takes a couple of seconds before it comes up with a reasonable estimate. Well, after a couple of seconds, frequency errors are already over, right? If we have to do it non-causally or not online, it doesn't fit whatever we do, because we don't want to do a voice search query and then say, please come back in 5 minutes and we'll tell you what you said, right? That's not practical to what we do. So trying to do such approaches that have been written, they frequently don't fit what we do, or they make errors where, we think if it's very, very reverberant, the localization goes off, you start beamforming in the wrong direction, everything falls apart. Right? So we've been sort of pleased by this approach where we say, we have our raw waveform model, we sort of extended it, and it seems to behave well in terms of doing these things implicitly, right? And so a lot of this, like I said, the localization, we don't know where it happens, but somehow it happens in the network, right? And that has been, it's partly disturbing because, you don't really have control over it, but, in terms of empirical results, it seems to behave very well. I listen to the boss, whoever gets the next question.
So you showed some results with the Oracle TDOA. Did you try training your network on the Oracle TDOA aligned?
These are all trained on that particular.
When you showed the trained one, I assume it was on the non-aligned waveforms, but you showed that it was better to train it on the raw data than to use the Oracle TDOA. And
no, the time-aligned one actually matches. So it shows that we don't lose apparently anything by doing the.
So the fixed one is you actually train your network on that, on the fixed.
There are 3 training experiments and testing experiments. So the first one, we give it a single channel, which is delay and sound based on the Oracle, right? So the second one, we still give it multi-channel, but we say you don't have to figure out how to do the time delay. We give you the shift for free, right? So we use the Oracle to.
So it's still a single channel. I was wondering about if you still keep a multi-channel.
The first one is single channel.
Yes.
The second one is multi-channel, but we time delay each channel based on we know the angle of arrival.
Okay.
And the last one, it has to figure out the time delay by itself.
Okay.
And as you can see, there's no difference between the two. So it seems to be effective at learning that.
Okay. So follow up. Did you try use your some layers somehow as input features to try to estimate the TDOA? I mean, are your features able to estimate? I mean, they look like they would be.
You mean that, right? So remember, the time delay is implicit in the filter and sum, right? Like I said.
Yes. Okay.
So here,
so it's just a matter of how you read it.
Right. So here it comes up with the filter weights online, whatever that. So it has to do that if you think shifting the time signal is important, which I think it is.
A clarification question. So the baseline, the very baseline was a clean speech, was the near talk is a 16 point something error rate.
So the baseline is an MTR system, right? So it is trained on various noisy conditions.
No. The reference, the reference result is like using the close talk Google search clean is at like 16 point something, right? That what error rate?
On the voice search set.
I tried to link different results together. So the reference, the original data set you used, and then add some noise on top of that, right?
So we're at about 10% when it comes to an actual voice search, which is close talking and And
that's a 10%.
Yes. So, but this is already a noisy version.
Okay.
And and with an MTR system. Right?
So so the sort of reference result is like a 10%,
right.
And when you add all this noise together, the best result that you can achieve is like 17% or 16.9.
Right.
Okay, good. Thank you.
So for the multi-channel raw waveform models, if I understood correctly, you trained them on 2,000 hours of training data, right? Do you have any experience if that also should work with a smaller set, or is it critical to have that amount of data for this model?
So I think the bigger thing is sort of what the rest of the system looks like, right? So we have this CLDNN that we always use, and we know that's very well tuned to the 2,000 hour set. So I think I have, again, we don't deal with that problem, so we haven't spent a lot of cycles on this. But I find it hard to believe that this is not additive to a system that is appropriately sized for a smaller data set. So if you have 100 hours, maybe you shouldn't have 3 giant LSTM layers and whatever it is, and train on that. Which actually would be interesting is to see if these representations are less chaotic, because the model at that point will have less modeling power, and therefore maybe it needs to be, have less freedom on how to represent whatever comes out of the input layer.
Actually, I would wonder what you would get on CHiME 4. Here was another question. Okay.
When you talk about this Oracle beamformer, I think you don't take into account that the signal is actually reverberated. Did you also try to take that into account, and then how would that Oracle
So
word
we did.
error rate look like?
The experiments here are just, we were quite surprised how well it worked, right? So we tried quite a bit with quote traditional approaches, and yes, find it hard to really work because there are errors made in localization and so forth. So we started doing this and sort of say like, well, we don't do anything and it seems to behave very well. So we try to analyze as much as we can by doing these things. So, I find it very hard to sort of take into account more variables without making it even more complicated. But so the time delay is something that, because of the simulation, we know and we can quite easily take into account. Right, the phase, you can either put it in or take it out. So those are sort of reasonably easy to do and insightful to see how it behaves. So can you do more? Probably, but we haven't invested a lot of time in this because all of these are. It looks trivial as a little box in a table, but these are like 3 weeks of running many computers, and so I don't know if you realize how many hours of compute you've looked at.
Thanks.
So my question is about have you guys ever listened to the signal enhanced? I mean, you guys are there are several ways to, like for example, using a multitask running, but they're basically using a cross entropy criterion to optimize this kind of the network part. So I'm very curious there. It is well the heard, or that's for me very interesting question.
I admit we are all real speech scientists who never listen to speech.
Yeah, that's actually my comment. When I started the ASR research, my mentor often told me that ASR researchers don't listen audio so much. So maybe we should listen a little bit more what happened. For example, in their complex frequency, the domain cases, the beam pattern seems to be very weird.
Yes.
And I actually had the same experience. The beam pattern is quite weird. I listened to some of the audio with the cross entropy criterion. That sounds very weird. It's not sound,
right,
but it's simply in terms of the cross entropy criterion, word error rate, it's actually improved. So I really want to know what happened inside. But low signal cases may be okay. Yeah.
I have debugged, when something didn't work, and sometimes we have these things that are synthetically synthesized. And, some of them are very, very noisy, and I can make out of it, but the recognizer gets it 100% correct. So there is, like I said, there's a giant neural network system on top of that learns stuff, and and we have very little insight in this. And I think it's also part of the weakness of these approaches that you lose insight in terms of what's going on unless you maybe can manipulate the variables that go in.
Yeah, question.
I'm Hiroshi Okuno, Waseda University. You insisted end-to-end modeling, but
I didn't insist. I'm just saying that's the direction we're going in.
Needs some social localization, maybe some speech enhancement. For example, we are developing a search and rescue robot with microphone arrays. In that case, sound social localization and speech enhancement are very important. So my question is, what is the performance of your sound social localization or speech enhancement compared to various conventional systems?
So a couple of things. So I think that the sound source localization is very important, and I think particularly in some conditions that we haven't looked at yet very carefully, which is the case of where there's multiple speakers. So if you think of this product even, I think it's likely that you have multiple people speaking in the same room. And having some insight of where the localization is pointing to would be useful, and this implicit localization is not the greatest thing. And so here we've just been driven by performance, and like I said, the early investigations into doing localization in whatever algorithms we have seen written up and attempting to implement them, sort of in the context of this 3-second utterance for which you want an answer instantly, it's very hard to make that work reliably, and therefore it will spoil everything else, right? Like if you beamform, if I want to process your speech and I'm beamforming that direction, it's not going to help, right? So So given that this sort of worked, we sort of been keeping on this paradigm. And again, so getting back to my initial point of the talk, I'm not saying this is the correct way to do it and everything else is wrong. And particularly with the context of the application, I think that, as you mentioned, localization could be very important to have explicitly. And therefore, this is a completely inappropriate model. But we haven't looked at it at the moment.
Yes. So the overall neural network has many outputs at the end, and I was wondering if you had some insight why the adaptive beamformer network cannot predict so many beamforming weights.
No. So well, maybe it's a matter of sizing, or I don't know. Maybe you want to answer? He's the real master of that system. So
it's not. It cannot predict a lot of parameters. It's just that we want to make a model size in the control, and we don't want to kind of expose the size of the model. And another thing is like because you predict a lot and it's frame based. So for each frame, you have to like generate solving of parameters. It's very sensitive to the errors in the prediction, which may make your system doesn't perform that well.
Okay.
I didn't want to negatively reflect on him because the system works quite well, particularly in the time domain, and so we were quite enamored with it. Just when it comes to speeding up the compute, it seems to not behave as well as the other ones, which is sort of an easy way. So that's, yes.
Yeah. How do you see data collection going forward? Is it something where you'd envisage collecting clean channels, one channel, and then doing simulation, or do you envisage sort of collecting 8 microphone data and
well, the thing we love is always when we have a real product where the data comes in, and the problem is always that if you launch a product that doesn't work at all, nobody's going to use it, right? So you have to. That's the conundrum that you have to go through. So this seemed to be a somewhat plausible system that works, and without saying anything, but we did announce this product, this Google Home thing, that at some point will come out, and then we'll have real data coming in. So that that's the data we like most because that's from the actual device, people actually using it, and from there on we quickly iterate by fine-tuning our models, etc.
Hey, so I'm wondering how confident you are that your system is finding a global optimum, and if it's possibly a local optimum, how sure you can be that the beamformer its finding is actually the one giving the best error rate, or if there mightn't be a couple of hundred beamformers giving equal error rates, or maybe possibly even better ones.
So we had this question many times, not just for this beamforming work, but just in general with neural networks, right? So again, I can only give you a fairly fuzzy answer, but you can imagine we run tons of experiments, right? Even though we have this 85 million or whatever it is, how many million parameter systems, no matter who I ask to train a system, they all come up with the same word error rate eventually. So in that sense, is that the only local optimum? I'm not sure, but the performance-wise, we seem to always sort of converge to the same point. And if you look at this, we have an adaptive, a factored, frequency versus time domain system. They all come out with more or less the same word error rate in the end. So, again, do I know that there is not some magic parameter setting where we get 10% better? Of course, I don't know. Otherwise, we would use it. But just from the fact of repeating the same experiment in different settings, getting to the same word error rate seems to indicate that we get somewhere.
And how stable are the beamformers? How much do they change from experiment to experiment?
So the only concrete evidence I have is if you look at those beam patterns we get from the frequency domain learned system versus the time domains, they're wildly different. And that is sort of surprising. And given that they get the same performance, like I said, it's compensated somehow by the system afterwards. So I think being in tune between the acoustic model and whatever you do in enhancement is the key. But, as you said, there might be many local optima. Yeah.
So if there's no further question, one last, because I think
a very quick question about selecting the data for your test set. A very quick question about how do you select your test set? Because if you're looking at the YouTube video or voice search data, many data doesn't have anything. Do you use everything that randomly sampled, or you deliberately choose something that has speech?
So there's a couple. If it's for YouTube, we have the system actually runs detectors before so we get these YouTube videos in. We do detection of speech at all, because a lot of them are music videos, so we're not going to process those. Then we do language ID to make sure that we have a recognizer for whatever comes in, and then we do whatever you want, right? So for the online, the mobile stuff, we know if it's from voice search, because you're talking to the query box, we sort of know that this is voice search data, and we can use all of that because likely you're doing a voice search. If it's an IME thing, the input method, where you might be dictating an email or something like this, we know that it's in that context. So we actually split data sets based on that. So all this is on voice search data because we assume that you're not going to dictate your email through the Farfield at-home device. It's most likely that you ask, how old is Barack Obama, or something like that.
But just to confirm, you still use the valid speech in your voice search data as
These
your
are all,
dataset?
yes. I mean, it's whatever came out of the system. I mean, it's been endpointed with the voice activity thing, but it was initiated likely by somebody saying, okay, Google, and then saying something, or pressing the microphone button and then saying something. And they're all, quote, valid utterances, yeah.
Okay, so I think
You
this.
said last, so shut up.
So I think this closes the session.